Okay, so in this video I want to give you some more examples of ends. So just first off, a straightforward generalization of the example we saw last time. So that was just about the end of the hom functor. So we can jazz it up a little bit this time. So we take hom, but we take hom of, we first apply two functors. Okay, so we just have f and g are just two functors from c to e. Then this gives us taking hom in e after applying f and g to the respective parameters. We see that we get a perfectly good functor from c up across c into set. Okay, and as I say, generalizing the result of last time, which was that the hom of the hom of cc taking the end just gives us the natural transformations of the identity functor. Here, if we just put f and g in there, we get the set of natural transformations from f to g. Now, this is an important result for many reasons, not least of which is that this, in the enriched context, between functors, enriched functors, you get an object of natural transformations rather than a set, and you can use this end construction to build that. Okay, so that's the first example. I'll leave that as an exercise because the proof is pretty much identical to what we saw in the last video. Okay, so the next example I want to give is uses that. I mean, uses sort of natural transformations between two functors, but it's of a specific form, and it's sort of a very baby example of Tannakian reconstruction. So let me make that into example 3 then. So the context here is we work in the category of sets, and we look at a monoid, and we look at the category of sets that monoid acts on, and we try and recover the monoid from that. Okay, so if I'll explain I'll state the result and then explain how we get there. So M is a monoid in the category of sets. We've got M set is the category of M sets, so the sets that M acts on, and we've got a forgetful functor from M set to sets. Okay, and the result is basically that the end, so hom, u, well, let's say S sigma, u S sigma. So they're just M sets. So that's a hom in set. So S sigma in M set. So this end here, well, from the result I've just given you, this is the natural transformations of the forgetful functor to itself. But the important result is that this is just equal to n. Okay, so we recover our monoid just by looking at the end of this forgetful functor. Okay, so this is a baby example of so-called Tannakian reconstruction theorem. So which says, well, in general, you'd look at monoids or algebras in categories other than sets, say in the category of vector spaces or something, and then this would be the representation category rather than the category of M sets. So you just look at the natural transformations of the forgetful functor and you recover the algebra object or the monoid object that you first started with. Okay, so this is sort of a baby example of Tannakian reconstruction. So this example I actually learned from the NLab. So do have a look at the NLab page on Tannakian duality. So what I'd like to do is actually just give you a proof of this. So that should be straightforward in this case. It's just an example of the Yonnet dilemma, really. Okay, so I guess I should explain some of the terms here. So M is a monoid in set, so that monoid is just a group without inverses, if you like. So if M is a monoid, what we've got is a product M cross M to M, and we've got a so this has to be associative in the usual sense, and we've got a sort of a unit map into M, which picks out the identity element in M. So eta of star is equal to the identity or unit element inside M. Okay. So that's a monoid in the category of sets. So what's an M set? So an M set consists of a set S together with an action of M on S. So elements of M will give you an endomorphism of Fs to itself. So this is the notion of action of group on a set is one of the first things you meet in the first course on group theory when you're learning sort of naive group theory, orbit counting theorems, all that sort of thing. So it's just exactly the same. So this has to behave nicely with respect to the product operation on the monoid, but I won't go on to that. And so these form the objects of a category, and the morphisms in this category of M set are the equivariant maps. So the morphisms are equivariant maps. So what is a morphism in this category? So we've got an M set S mapping to an M set R row. So it's just going to be a set map between the underlying sets. So it's going to consist of a map S to R, which commutes with the action. I won't write that down. So commuting with the action of M. Okay, so these are our morphisms in the category. The equivariant maps. Pretty standard construction. Now we've got this forgetful functor. So now this forgetful functor, so what does it do? It just forgets that we've got an action. So a set and an action just goes to the set S. Now this is a representable functor. So this is a functor to the category of sets, and it turns out to be representable. So which object represents it? So let's go here. So a perfectly good M set is M itself. So we can take the left regular M set. It's like the left regular representation of the group would be the group acting on itself essentially. So ML. So this is the M set, where the underlying set is M, and the action of M on M is just the product. Okay, so product goes from M cross M to M, of course. Okay, and that gives us a perfectly good M set. And this actually represents the forgetful functor. So HOM in M set from ML to S sigma. So what is that? Well, so this is just a set of equivariant maps from this left regular representation, this left regular M set, I should say, into S sigma. Turns out there's a map to S. So if we have an equivariant map, we can just see where F sends the identity element inside the monoid. Okay. And that really tells you everything you need to know about the map, because f of m for any other element, so then we have f of m is equal, so that's the same as f of m acting on E, so just using the regular action. F is equivariant, so that's just m, the action on S, on f of E. Okay? So we can determine f of m from f of E. So that tells you everything we need to know about F. But it turns out this is a bijection. You can hit any element of S in that way. And what is S? Well, that S, another way of saying S, is just the underlying set of the M set F sigma. Okay? So that's another way of saying that is that ML represents this functor U. Okay? So U equals hom ml blank. Okay, so that should now be enough setup in order to prove this now. Okay, so just with an application of the Unay dilemma. So that's what we've got to try and show is we get m there. Okay, so the set of natural transformations is just then the set of natural transformations from hom in m set ml blank to hom in m set ml blank. Okay, so that's just using the fact that u is representable, but now just essentially application of the Unay dilemma. Well, actually the dual of the Unay dilemma, these are actually not pre-sheaves. I mean, so normally with the Unay dilemma you get an op there, but I mean it's the dual of the Unay dilemma. That's just the that's just going to be this evaluated on the representing object. So that's just going to be hom in m set from ml to ml. Well, we know what this is. Of course, hom from ml into anything is just the underlying set of the thing. Here, the underlying set of the left regular m set, well, that was just m. Okay, so that just gives us m straight away. So this shows us that the set here is the same as the set m. In fact, with a little bit of work, not too much work, you can show that this is actually a monoid. The natural transformations from u to itself is a monoid, and that recovers the monoid structure on m. So as I say, I mean, this is a sort of baby Tannakian reconstruction theorem, because just from this so-called fiber functor, this forgetful functor from m set into set, by taking this certain end, you recover m. Okay. So I'll leave that there for now.